We've been talking a lot about the idea of conservative vector fields and potential functions, and there have been examples to where given the potential function we can find a conservative vector field. But what about going backward from that? What if you're given a conservative vector field, or what if we're given a vector field in general? How do we know it's conservative? And then secondly, if it is conservative, how can we figure out what the potential function is? Because if we have the potential function, then we can just use the fundamental theorem of line integrals to be able to evaluate f dot dr, the work that goes through that vector field. So let's suppose that we have a vector field of this form, p of xyi plus q of xyj. And let's assume that it's conservative. If P and Q have continuous first partials on a domain D, then we can take the partial of P with respect to Y, the partial of Q with respect to X. If those are equal, then the vector field is indeed conservative. All right. So once we know that, then we can start to find what the potential function is, or the original potential function is. So we have a slew of examples here to where we're going to go through. We're going to determine if a vector field is conservative. If it is conservative, then what we're going to do is to be able to find the potential function. All right, so in our first example, x e to the yi plus y e to the xj. So let's define the first function in front of I as p, and then the second function in front of j as q. So the partial of p with respect to y is going to be equal to x e to the y. The partial of q with respect to x. Okay, so the partial of q with respect to x is going to be y e to the x. And clearly these are not the same. So what this means is that it is not conservative. And that means because it's not conservative, we can't find the potential function. So we cannot find potential function. All right, so then we just skip on to the next example. Now in the next example, we're going to see that this one is indeed conservative and that we can find the potential function. All right, so as our second example, let's define 6x plus 5y is p. Let's define 5x plus 4y is q. The partial of p with respect to y is going to be equal to 5. The partial of q with respect to x is also going to be 5. Notice that these two are the same, so for part A, we can see that since these two are both equal to 5, we can say that this is conservative. So, or we could just say F is conservative. All right, so now that we know it's conservative, now we go through and we do the million-dollar question. How do we find the potential function? All right, so we're going to take P, and remember, this is a derivative. Okay, so remember, phi of x should be equal to P. Phi of y should be equal to q. All right? And if that's true, that means we found the potential function for this conservative vector field. So here's what we're going to do. We're going to take and we're going to integrate p with respect to x. Now, of course, we could integrate q with respect to y, and we can still get to the same answer. Okay, so let's just go ahead and we're going to say that phi is going to be equal to the antiderivative of 6x plus 5y with respect to x, okay? Because remember, phi x is equal to 6x plus 5y. So if we take the antiderivative with respect to x, it's going to help us to get to the original phi. Not too difficult. This is going to be 3x squared plus 5xy. Now, usually we say plus c. However, there's going to be some unknown function y because we took the antiderivative with respect to x. And we know the derivative of g of y is going to be 0. Okay, so Every time we do these types of problems, there's going to be an unknown function. It just depends if you're integrating with respect to x or y, and you can do it either way. Now, let's now find phi of y. So in other words, we're just going to take the derivative of what we just found. So that's going to be equal to the partial with respect to y of 3x squared plus 5xy plus g of y. And that's going to be equal to 3x squared goes to 0, 5x plus g prime of y. All right, so there's a derivative of some function, g, which we don't know what that derivative is, so we just call it gy. However, phi of y is right here. So we know that we can set this function equal to 5x plus 4y. Now what we're going to do is we're just going to say, okay, well, to solve this, both sides have a 5x, so we cancel those out. So g prime of y is equal to 4y. And what we're going to do is we're going to integrate both sides with respect to y. All right, so if we do that, then g of y is going to be equal to 2y squared. And so our potential function, we go all the way back up to the top. Remember, this is our potential function. We just solved it for gy. All right, so phi of xy is going to be equal to 3x squared plus 5xy plus 2y squared. Now, what if we don't believe that? All right, well, if we don't believe it, let's find phi of x and let's find phi of y. And then we'll see what those equal to. Well, phi of x is 6x plus 5y. Phi of y is going to be 5x plus 4y. 6x plus 5y is the original p. 5x plus 4y is the original q. And that's how we know we're right. Okay, so that's going to be our potential function. Okay, and what does that do for us? Then we can use the fundamental theorem of line integrals to be able to find f dot dr over any initial and terminal point. All right, so pause this, maybe go back through, make sure that those first two examples make sense, and then there's two more subsequent examples of a little bit more rigor after this.